Okay, so a system of linear equations is homogeneous when the right-hand side is 0, so all of those entries are zeros. And then, as you can see, so the augmented matrix then stops being augmented, because you don't have to do anything with that last column. If the last column is made of zeros, we do our elementary row operations. What's going to happen to the last column? Nothing. It will be still made of zeros. So there is no reason for us to track it. So we will concentrate entirely on the matrix itself. So that's one of many reasons why homogeneous systems are worth studying as a stepping stone, but still they're just so much easier to understand. Okay, so as I pointed out, so always has at least one solution, that is 0. This is the proof right here. So just multiply by the 0 column and you end up with a 0 column. Those aren't ones. It's just this thing that doesn't do the right dot. Okay. So 0 column for the input variable will produce the output 0 as well. So that is still to be discussed at length. That is the property of linear functions, as a matter of fact. So if you remember, the main idea about matrices, that they are functions, and in particular they give you 0. If you plug in 0, you will have 0 as the output. Okay, back to the solution set. A homogeneous system has at least non-zero solution, but they all will be, as discussed in the previous slide here. Well, actually, there's an error here. I missed one option, point. So they're all copies, as you can see, they're all copies of Euclidean space of all possible dimensions. So if the space of unknowns is n-dimensional, then all spaces, Euclidean spaces of dimension less than or equal to that, are possible. So Rn, starting with nothing over here, and ending with everything. So it could be nothing, could be point, line, space, and so on. Okay, so that is a hierarchy of the sizes of the solution set, starting from nothing to nothing, from nothing to everything. Okay, so that's what it is. And in fact, you can do more here. You can have that hierarchy can be more specific. So n is equal to 3. So then the empty set is the possibility, the first possibility. But let's make specific and just take some of the possible solution sets. So it could be 0, and then that's one zero-dimensional. Okay, zero-dimensional here, zero-dimensional solution sets. Then one-dimensional solution sets, they are lines. In particular, what are the most interesting lines in the three-dimensional space? The axes. So in particular, x-axis could be a solution set, and y-axis could be a solution set, and z-axis could be a solution set. There are all kinds of other lines as well, but these are the three. And as you can see, the point that I'm trying to make here is that they all contain that 0 over here, like this. Okay, so 0 is contained as a solution set contained in all of these. And then if I move on to two-dimensional, those are planes. What are the most interesting planes? Yeah, so the coordinate planes, xy, x, the yz plane, and finally zx plane. And once again, I could draw arrows. So x is a subset of, let me try to, this one is missing it. Let me try to stretch it a little. Okay, so I could also go from x-axis, I could go to xy plane or xz plane. Okay, from y-axis I could go to xy plane or yz plane. And from z-axis I could go to z-axis or z plane. So as you can see, we have this is kind of growing hierarchy of subspaces, is what they call. But there's only one three-dimensional subspace. It is the space itself. So, like this. A pretty diagram. Hierarchy, not just a list as you can see at the top, but actually there is some kind of a, there's only one possibility at the bottom. This is three-dimensional, so that's why it's not growing in the middle as you would as elsewhere. So just look at it. So you go from 0 to 3, from 1 to 3, then to 3, and then to 1. Okay, but if you take four-dimensional space, you'll have what you're going to have is n is equal to 4. You start with 0, and then you have 4 axes. How many planes? No. No. 4. How many pairs? How many pairs? This is discrete math. So how many pairs? So we have 4. Yeah, you have 4. How many pairs? You just draw it like this. Okay. It's 6, is it? 6. 6 pairs. So and then so each of the x's will be a part of 3 planes, like that. But then and then there is a third dimensional there. They progress to every plane is a subspace of a three-dimensional space, so there will be more branching, and then but at the end they also end up with the whole space. Okay. So the point of this is just first of all to show you the hierarchy, but also I want to make contrast with this, which is only gives you a sample of possible solutions, very simple solution sets. So when it is an axis or it is a coordinate axis or coordinate plane, this is a very specific kind of equation, a very specific kind of solution. We can have any line, we can have any plane. Okay, so that brings me to this discussion over here. No, this one. Okay, so an example of a plane solution set as a plane is given here in the four-dimensional, or just in three-dimensional space. It will look exactly the same. Okay. But if it is a homogeneous space, then remember when it is homogeneous, S is equal to 0, so it is a bit simpler, so you don't have to make that shift, and then your plane will contain the origin. Okay, so slightly easier life for us. But what is interesting here is it is a plane. We know that a plane is a copy of R2. So this is a copy of R2. Copy of the two-dimensional Euclidean space, which certainly if you look at it you know that it is. But what about algebraically? In what sense algebraically it is a copy of R2? And that is the axes. You can see the axes, right? So this is certainly not xy plane, right? So xy plane is elsewhere somewhere, but it is a plane, and you can analyze it algebraically if you point out the axes. And we already plotted the axis, not by accident. So, so if it is not an xy plane, how would you call this? How would you call this plane? It's not an xy plane, but let's look at the writing there.
I'm not sure what you're looking.
I'm just wondering if you can think of a good name for this plane. All close. TS. It is the TS plane. Why? Because these are the two variables that give you the location on this plane. So on the xy plane, x and y give you the location on that plane, right? Now we have built a new plane, and then if you look at those two lines, and that especially that equation on the right, TNS as lowercase will give you the location on this plane, right? So it is TV plus SU. So if you know T and S, then you will know your location, right? So because V and U are specified by our system, they're fixed. But T and S vary, just like X and Y on the XY plane, and so this is just a name for a TS plane. Not that there's anything important about this name, it's just a point out in the right direction of what we're going to be doing with the spaces in general, not necessarily solution spaces of linear systems, but in general, the planes will have to be treated as copies of R2, and in order to do that, we have to point out the origin, which we already pretty much took care of it, so they have to pass through the origin, but also you have to point out what are the 2 degrees of freedom, and the 2 degrees of freedom for this plane are S, and T. Okay. The one thing also long term is important to observe the relation between these two lines. These two lines serve like the two axes of our plane, right? But what is the angle between them? Can you say anything specific about it? It's a trick question.
Well, we say 45 degrees.
Why 45 degrees?
Well, you got two of the sides that are the same size. They're
no, that's not what I meant. I was drawing just whatever I felt comfortable. So whatever you see there is really not to be read as the truth. In fact, they're determined. The plane is determined by those two vectors V and U, as you can see them over there. So the question about what's the angle between the two axes is the same as what's the angle between V and U. Can you say anything specific about it? No. Oh, the answer is no. You cannot say anything specific about it. You can end up with any imaginable pair of vector U and V, any imaginable axis, and any imaginable angle between them. Okay? The point being that they do not have to be perpendicular. So what we have learned about XY axis, that's where a Cartesian system starts. You start with two axes perpendicular to each other. Then in linear algebra, we also made it analyze it with vectors. But this time we can see that in the future this is the best way to represent this plane is by that formula on the right. But the axes will not be perpendicular. They don't have to be perpendicular anymore. Perpendicular, so the angles are important, but really not as much as you think. So being non-perpendicular gives you totally the same control, same linear algebra as before. It is hard to point out something real life tangible thing that it was easy to point out the axis, the three-dimensional space. These two black lines give me the two axis and the vertical corner the third. Okay, so but they are all perpendicular. Where in real life do you see axes that are not perpendicular and like this? And the answer is not frequently. In some modern architecture, sometimes they allow themselves to have not 90 degrees angles, but it is uncommon. So it is a jump from a leap of faith from the Cartesian system, and we are so comfortable with it. 90 degrees angles always, but it is really doesn't have to be this way. So all we have to do is just make sure that this is fine. It doesn't have to be like this. It's hard to make with fingers. So the 90 degrees angles, you can have them like this. It will work out just as well. The algebra is the same. Okay, so you can't have coordinate system with respect to vectors that are not perpendicular. The only trouble is the dot product. The dot product will have to go because it relies on perpendicular representation. But the rest is okay. So we can add, we can multiply, all the scale and multiply, all of this will work out just fine. Yes.
So this is moving away from the Cartesian system.
We will, yes.
So this is like the slow getting away from. Is there like a name for that?
There's
It's just getting.
right. So Descartes invented Cartesian system. It was named after him. It was later realized that you can have we will be speaking of a basis. A basis of a space is made of as many vectors as necessary depending on its dimension, but they do not have to be perpendicular to each other in order to represent every other vector in the space. Okay, so yeah, that's what we're going to be talking about, a basis of a space. So you can have, think about in the Cartesian system, you can have this or you can have that. They might be two different coordinate systems, even they are all perpendicular. So there is already so much variety that that you should be prepared to deal with what? To deal with the change of coordinate system. Okay, and then what even can happen is that what if the resulting system is not orthogonal. You may have seen, anybody took calculus 3? Yeah, so you might remember computing volumes, right? So what do you do if you want to compute the volume which is not, or a function on the volume which is not a box, but rather something like this, whatever it's called. I don't think there's a good name for it, but you can imagine roughly what I'm talking about. A skewed box. Once again, other than short of modern architecture, I cannot think of where else you can see a box that is kind of crushed. Anybody? What? No, yeah, that's what you do in calculus 3. I'm just wondering if in real life you encounter something like that.
You just like break it up because
Yeah, well, yeah, you just crush it. Well, maybe cells in packaging, or maybe plants, cell of plants. You know, they have weird shapes, not necessarily perpendicular. All kinds of weird materials that are made of non-uniformly. So if you have a fabric, you have it like this, right? But you can do it like this, right? A fabric, two threads could be perpendicular. That's normally it is done, but you can go like this as well. Okay, and that kind of automatically creates your two-dimensional non-Cartesian system. Okay, so we'll get to that. That's the next. Well, not the next topic, but. We still have a debt to this previous topic, and that is Gaussian elimination, and pretty much the algorithm of solving systems of linear equations. It lists an outline. So let's do that. So Gaussian elimination. Which means that we have already made that step as to converting our system to its augmented matrix. Okay, so and then we know what we're after. Find its reduced row echelon form. Okay, so how? Well, the answer, the short answer is we already know. It is the elementary row operations. So these are tools rather than, so it's still not an algorithm. So let's list them, at least. Number one, replacing a row with its non-zero multiple. So remember that if you want to create a leading one and you have 3, you divide by 3. Okay? So, or you multiply by 1/3, which is the same thing. The only thing you're not allowed to do is to multiply by 0. Why? Why are not we're not allowed to multiply a row by zeros? What?
Just get you all zero.
Yeah, so but why is it bad? Well, let me give you an example. X plus y is equal to 1, just an equation, x minus 1 is equal to 2, and then I multiply the first row by 0. So it will be, there is nothing wrong with this equation.
It's just
What?
not equivalent.
They are not equivalent, right? It is, you're likely to end up with an equation that, the system that's not equivalent to the original, meaning it has a different solution set. And we don't want to do that. Because the process is very long, and you don't want to keep track of everything and go back and verify everything. You want to carry out the operation that at every step you'll have the same exact solution set. So that's why you're not allowed to multiply by non-zero 1. The second one is also more subtle, seemingly similar, but also keeping in mind that extra requirement that we have in mind. So replacing a row with its sum with a multiple of another. Now I'm looking at it, I think number 1 is included in number 2. Replacing a row with it, no, it's not included. So multiplying a row by non-zero multiple, not other rows are not involved. So it is necessary, but it's not the same as number 2, which is we using it for eliminating things, right? So if you already have a leading one, for example, what do I use it in order to create zeros? Okay, so if I have 3 here, I have 1 there, say this is R1, R2, right? Then something going on elsewhere, doesn't matter, but my next operation will be what? I replace R2 with. I don't replace R1. R1 remains the same, it has a leading 1. So I'm replacing R2 with what?
3 times. R1.
That's right. R2 minus 3 times R1. Right? That would create a 0 at that entry. Right? So that's the second one. And there's the third one, kind of subtle. Interchanging rows. It's is it optional? Yeah, it's not really optional. You might interchanging row means simply interchanging equations, right? Nothing else. So certainly totally legitimate. There are no computations involved. The solution set remains the same. And but you do need it sometimes. For example, you might your first equation might be made of all zeros, and what you want to do with those is put them at the bottom. Okay, so all right. So then the theorem, as I alluded to, the solution set under elementary row operations. Remains the same. Okay. It takes some proof, but really not a lot. So certainly number 1 and number 3 are obviously do not change the solution set, right? Number 2 a little bit might require some work, but we'll just take it for granted that once again everything works out fine. There is just worth mentioning. The next one, there are corresponding elementary column operations. Whoop. Interesting. not that fast. Elementary column operations. Same 3 column operations. Okay, so I only care about number 3 primarily. Interchanging columns. What does it do? It only interchanges the location of the variables, right? So as long as you remember that, you are okay. Remember that you have changed the order. It is convenient sometimes. So once again, if you're solving an equation, then you feel free to interchange things, because I mean, maybe you already have a leading one in the last column, so you want to make it a leading one by moving it forward. Okay, so like this, 5 3 0 0 1. Well, how about this way? Okay, if this is your matrix, then you want to put the first column in front. Well, I don't think it's a very good example. Okay, so 1 2 3 0 0 1 1 2 3. Oh, maybe like this. Maybe this is your matrix, and if you put the last row, last column in front, look at it. You are halfway there. You save your time. As long as you remember this is x1, x2, x3, and it becomes x3, x2, x1, x2. Okay? So that's an elementary column operation. Okay, so once again, it doesn't do anything. If you start doing algebra, that might doing algebra with elementary column operations, the other two will also solve you the problem, but it will be a solution with respect to different variables. Okay, so whether or not it's what you want is to be determined. Okay, so what is the plan of accomplishing what we want, finding the reduced row echelon form? And the answer is, well, there are 2 steps. First, find the row echelon form. Number 2, find the reduced row echelon form. Okay, so remember the row echelon form is just is a staircase and nothing else we are saying about. So that's a row echelon form is a staircase of zeros with something on top of it. That's a row echelon form. But the reduced row echelon form also gives you extra columns of zeros. So this is the very much an outline, but think about like it's a modular design of an algorithm, right? So this is how we're going to proceed, and then you create more and more modules inside of these. Okay, so you just elaborate. So you take stage 1, so you can call it a stage, and then explain how you gonna get where you want. So the plan is, well, here's the plan. So the plan is this. So I will ignore the last column in my augmented matrix, and so if ideally this is what I end up with, I will be order of I have to clear the bottom, not the bottom, but the staircase have to be made of zero. So I have to clear things out there. This is how I'm going to be moving like this. Like this. So columns from left to right, and within each column, top to bottom. Okay. Okay, so that's roughly the plan. So you take care that it's important. It's important because if you have taken care of the first column and you have a bunch of zeros, then when you move on to the second row and you start doing elementary operations once again, nothing is going to happen about the first column if you are not involving the first row. Okay, so this is step 1. So this say stage 1, and step 1 is this is what I want to have. Just take care of the first column. And just in case I put leading 1 at the top. So step 1 for the very first column, this is what I want to have.
For just row echelon form, does it have to be a 1, or did you say
it doesn't, but I think it's a better idea just to have 1. If it is, you start with a column, a row, the first entry in which is non-zero, and then just divide and make it 1. I mean, it's, once again, remember, it's a computer doing it, so we are right now not concerned with how hard it is to do, and maybe there are shortcuts that you would as a human see if you do it by hand, and you certainly want to take those shortcuts, but for a computer probably not. So you just try to make it as simple as possible, maybe simple as possible to write and explain rather than to actually do it. So you end up with some possibly ugly numbers, but that's okay. So that's what we're trying to have at the end of step 1 is this. So once again, a column with the very first column, it becomes 1 followed by zeros. Okay. So how do I proceed to stage 2? This is how, or step 2. I will cut out the first row and the first column. So that I would not by accident use them. So from my original matrix, I take care of the first column, which means 1 followed by all zeros below it, and now I concentrate on entirely on what's left. So drop first row, first column. Okay, so that then it's not that's not what I meant. Draw only. Yeah, I don't think I want to explain it this way. Well, what I'm saying is that you could. How should I put it? No, hold on a second. Yeah. No, that's right. I was right. Yeah. So drop the first row, first column, and then repeat. Repeat step 1. So once again, you will end up with with this 1 followed by zeros. There are some extra steps in between to take care of, because there's a possibility that you don't have the second row does not have a non-zero entry in the beginning, and then you have to do what? You have to interchange the columns. But generally speaking, that's the idea. We are it is what's the word? The recursive procedure. Right, so we reduce the size of our matrix by 1 row by column, and then proceed to do everything as before. Once again, to confirm that it makes sense is to ensure that first of all we do not need the first column. We don't need the first column. So if I want to create these zeros over here, I don't need the first column. I need this. I don't need the first row. I only need the second row. Okay, with this leading 1 over here, I need this leading 1, but nothing else. Okay, so if I have a non-zero entry in the second row, second entry in the second row, which is that what, yeah, divide by that number, end up with 1, that creates a leading 1, and then I'm using this leading 1 to eliminate all of these entries below it. Okay, so just the same as I did in the step number 1. Okay? Circular. And then, so that's number 1. Number 2 is that why am I justified cutting out the first column? Because I can promise myself that I'm not going to be using the first row. That's up to me. But the entries below it in the first column would belong to the rows that are still here. So why are we not concerned? Because those entries are entirely made of zeros, so doing any operations with them will still produce zeros. So we are nothing to worry about. Okay, so well, that's pretty much the outline of that procedure. It is a module of stage 1, and it is pretty much two-step cycle, right? Not a two-step cycle, but rather a cycle made of 2 steps, and then how far you have to go until you run out of rows. So repeat as many times as rows. Okay, so go and cycle. So once again, you will have to need here I mentioned that interchange columns if necessary before you proceed, so that you would have a 1. You can actually that's not necessarily entirely required, but I think it is. It's at least one of the versions is exactly that. So the end result is this. It's not just a staircase, but with leading 1s, but it is a perfect staircase, not without any kind of rest areas, stops, like this. Okay, so that's the end result of stage 1 is a row echelon form with leading 1s. The staircase is made of zeros. Once again, ignoring the right hand side, the last column. Even though at any point you can stop and see if you have 0 equal to 1. So if you don't want to waste your time, but once again we overlook that. Just for simplicity's sakes. Okay, so any questions about this? So stage 2. From here we got to arrive to a row echelon form. The plan is pretty straightforward. This time we're moving right to left and top to bottom. So everything is the opposite. So this is how we're going to proceed like this. Remember that above, for reduced form, we need zeros above each leading 1. So we proceed to killing them one by one using that leading 1 just as before. Just as in the stage 1, we're using it to kill those. But once again, you have to do it in the right order. Does it matter? For some reason, I'm thinking that you probably, well, if we look at stage 1, what happens if I do in the wrong order of columns? I think it's still possible. Well, no, this one is definitely, if I try to eliminate the very last column, that 0 under the leading 1 over here, if I try to eliminate 0 underneath, and then move to the left, what's going to happen? I think I think we won't. We will. We might mess it up. Well, anyway, I think I'm pretty much out of time. So so I'll just okay. So we'll continue after the test. And well, that's all I have to say, I think. So email me if you have questions about the test. I'll try to reply as quickly as possible.